So let me maybe start a bit on MacFlow. Okay. And it's gonna be called push Relabel algorithm. So let's start with some basic terminology. Okay. So let's say that you have a graph, it's directed, and it has capacity C. Okay. And I'm gonna use this backward edge here to denote the reverse edge of our thing in the graph. So now we are trying to solve flow problem, and we're gonna have like source not waiting and sink not waiting like before. Okay. And we have F, which assign the number to each edge. Think of it as like a flow, basically. Okay, and there's this concept of residual graph. Okay, residual graph GF is just defined from G and F. Like given G and F, the residual graph GF is the following. For every original edge E, right, you're gonna create a forward edge E in this residual graph. And the capacity is something like the capacity minus the flow. For example, this edge here, you have the forward edge here, okay, where the capacity, the residual capacity is 20 minus 5. But you also create a backward one. Backward edge with capacity, residual capacity, the amount of flow, which is 5 here. Okay. So the idea of residual capacity is, I think you have seen this. And the idea of residual capacity is just that it's remaining capacity. Okay, you have used up 5 from 20, so this is like the remaining capacity to send something through this edge is 15. But at the same time, now that you have sent 5 flow from this direction, you have a chance to cancel the flow by 5 units. So that's why we add this. In residual graph, you define this edge with capacity 5. The meaning is just the amount, how much you could cancel the flow that you have done.
So wait, do you differentiate, like in the residual graph, like edges that represent more capacity, edges that represent flow that can be canceled out, or is it the same thing?
Say again, sorry.
Like how do you differentiate, like in this graph, edges that are, like represent more capacity, edges that represent like flow you could cancel out, or is that not like a meaningful thing?
The differentiate between edges that have.
They do different things, right? The edges where they represent different concepts.
You mean the backward and forward one? So you don't need to distinguish them actually, because it's like it's really like if I send some flow along the backward one, it really kind of mean like I would not this. We will work actually on this graph, and we'll be kind of oblivious whether this is forward or backward. But the meaning in sending flow along the backward one, when we can map the meaning back to the original one by saying that if we send flow along backward one, it means we basically reduce the flow. Yeah. And we send here forward one, we increase the flow. Yeah. Okay. Yeah. But that's the kind of beautiful thing about residual graph is that we actually don't need to keep track whether like this is forward or backward. We just kind of work on this one. Yeah. Okay. And we will just actually keep only edges with strictly positive capacity. For example, if we have this for this edge here, right? I only have backward edge 5. There's no forward edge of 0. We remove it. Okay. So that's residual graph. Okay. And by the way, like we will use this. This is standard terminology, forward and backward. Okay. But note again that this forward-backward thing really just refer to the original edge orientation. Okay. Later, soon, right? We will actually, like in push label algorithm that we will look at, the vertex will have label. So you will have like label 0, label 1, label 2, okay, label 3. And some edge can go in this direction. Meaning that like if the level of U is more than level of V, so this looks like forward edge. But when I use forward edge, I don't mean this, right? It just means like whether it's like what's the orientation with respect to original graph. But here we will like if this is just some edge in residual graph, this edge here could be either backward or forward edge. It's just the edge that like let's call this downhill edge. It goes from like 3 to 1. Okay, it is downhill edge, so that you don't confuse it with forward one. Okay. Okay. Good. Okay, and we have a concept of net flow, which is the same thing that we have seen. Net flow out of V is just total flow out of V minus total flow into V. So that's the normal. But now here's a 2 new concept. Okay. Residual source or excess. I'm gonna call it excess quite often at V. Okay. So this is what? This is like kind of residual source with respect to F at V. So what is this? This is basically the initial source minus the sink at V minus the flow that go out of V. So, but I said that if this is less than 0, I just say it's 0. So what is this? It's just basically the amount of unit of source that I didn't send out yet, and it's not absorbed. This is a source that is not absorbed at sink yet, and didn't go out of V yet. So, okay, like it's like there's a node here. This is like a source. There is like sink here, and the thing that it goes out, maybe 3, and this is 9. So this would be like minus 3, the one that go absorb here, 3, the one that go out, and the remaining, maybe this is 10. The remaining here is 4. So the residual excess. The residual source here is 4. Okay. And residual sink at V is just, the sink that is not like that doesn't like get absorbed by the initial mass. And also plus the amount of thing that go into that go out of V. Okay. So it just basically measure how much the node V can absorb more. Okay. So we want to just send excess to residual sink. That's kind of the intuition. Okay. Now we will work with the concept of preflow. Okay. Intuitively, a preflow is just a flow that some mass from the source doesn't reach the sink yet. Okay. So, like if I have a graph here, and if it is S and T, and if I send 1 unit of flow from S to T, that's like ST flow. So I reach from source to sink. But maybe if I have another path and it kind of stop at V, that's like basically I send the flow to V, but it doesn't go to T yet. That's preflow. It's before it's become a flow. Okay. And basically, if I send from S up to V, then now V here have excess, right? And we want to send excess to the sink. That's the intuition. And here is the formal definition of preflow. It's really, it's just as simple as saying that the preflow is such that for every node V, the flow that we send out of it in total is at most the source at V. So we never send more than we have. So no deficit. That's what it means to be preflow. But in like what this is a formal definition, but like what's important is this. The important thing is that we basically allow excess in preflow. Some node V could have excess on it, like this one. Okay. But when a preflow has no excess, okay? Suppose that I have a preflow F, and suppose that there is no excess left. That is, every node here have no residual source. There's no excess. Then actually, F is going to be precisely the flow that saturates the source and respect the sink. So before I don't think I will prove this, but it should be something that at least intuitive to you. Like, so think like this, right? Like I have some source. I have source. Sorry. I have sink. Okay. And the goal is like to send the source from the source to sink. And we're gonna send the flow from the source, and maybe it doesn't reach the sink yet. So that's maybe a preflow. And if it doesn't reach the sink yet, then basically there are some excess. This will be the excess. But if there is actually no excess, then it just really means that we basically send everything from the source to some sink. All the source have reached the sink. And basically we saturate all the source. All source is sent successfully. And it will respect the sink because we respect the sink. Okay. This is like a kind of intuition that you should have, but it can be proved formally. Like just recall the terminology from lecture 12 and then you can confirm it. But I will not do it in class. I will ask you if you have questions like about this intuition. Is it intuitive to you at least? Okay. All right. And then there's the notion of augmenting path. What is this? It's just a path in is the path in the residual graph, right? From excess to unsaturated sink. Why do we call it augmenting path? Because if there is such a path in GF from some excess, to sink, then it means that if we send a flow along this path in residual graph, it will basically increase the amount of flow that we send, right? Are we good or? Okay. 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 So like if this concept of augmenting path is not so familiar to you, then I recommend look at my lecture on MacFlow, the one that I kind of asked you to watch some times ago. That will help. Okay. It's just a path. Augmenting path is like the intuition of augmenting path is just a path such that if you can find it, you can increase the amount of flow. Okay. And here's just if you can send from some excess to the sink, then you can increase the amount of flow. Kind of the intuition is like you have a source here, you send up to this point, so this point is excess. But if you can send further from excess to sink, then you basically successfully send flow from source to sink. Yeah.
So it's like any path.
Any path.
And it's like for any path, we're guaranteed to be able to increase the.
Yeah, because the capacity of every edge in residual graph is positive. So if there is some path in residual graph, you could increase the amount of flow. Okay. And the value of the preflow is just the total source minus the total excess. Right? This is like the total thing that you could have sent. This is the thing that you didn't send. You didn't successfully send to sink. Total source minus total excess is just a thing that you have successfully sent to sink. That's the value of the flow. And there is a fact about MacFlow min cut, right? So if there is no augmenting path in residual graph, then this preflow will have maximum value. And that's intuitive again. Like there is no way to increase flow. So that's its maximum. So F is maximum. And and also like although we are working with preflow, we can kind of turn back the preflow to flow, to the one without excess. So flow, when I talk about flow, it's just preflow without excess. Yeah. Okay, so given a preflow F with some value, okay, sorry, I mean with value maybe f here. That's what I use, value of f. Okay. Then we can actually extract the flow, the one without excess, which is like a kind of sub flow in the sense that this is at most f for all e. Okay. Such that this flow still respects the source and sink and the value is the same in linear time. Okay. Like the idea is like if you have some preflow, like if this send to sink, this is source, but there is some flow that kind of just stop at excess. You can just kind of track back each excess to the source and remove this part. Then you get the flow. So that's like you can do this in linear time. So like although our endpoint might be to compute the flow, I would just work with preflow now and just try to get a preflow with maximum value. It's the same as getting flow with maximum value because of this. Okay. Right. Questions about this concept, preflow? Okay. So yeah, on Friday, what we're gonna do is we're gonna basically show the algorithm, which is like really simple. The algorithm is just it's gonna be super similar to shortest of meaning path, decremental shortest path. It's just that you initialize the label to be 0. You maintain the flow, this preflow f. Now you maintain type H in what graph? Not in G, but in the residual graph. And the idea is just as long as there is some node that is not dead yet, it's not at the maximum level, and there is some excess, then you just try to push flow forward until you cannot. And that's the algorithm. Like if the x-axis, I'm gonna repeat this tomorrow, but if the x-axis and there is a way to, if there is an active edge out of it, then push that through the active edge, like send flow. But if there is no active edge, then make it increase the level so that you can find some active edge out of it. Do this until you cannot do. That's going to be max flow algorithm. So you see the difference is just previously in shortest path, what we do is just as long as there is some node that is not dead and it has no active edge out of it, you pull it, you relabel it. Now it's not quite that. It's just asks if there is some node with excess, because the goal here is just to remove all the excess. If there is some node with excess, then there are two cases. If there is the edge, tight edge out of it, then push flow. Otherwise, relabel it. So yeah, so you see this is so simple, and this simplicity basically why this algorithm is basically used in practice. Okay, we see the correctness and analyze this algorithm tomorrow. Yeah. Okay, see you.